Welcome to this lecture. It is on molecular separations. Biotech products often have a mixed set of properties. Like in the example shown, there may be polar and non-polar groups and negative or positive charges depending on the pH. Besides, the molecule may be unstable. Often, it's not easy to find the physical properties and stability data. However, we need a table like this one to determine how molecules in a broth can be separated. If we see key differences between physical properties, the bottom row shows separations that can exploit those. Log P octanol water is a measure of hydrophobicity. Boiling and melting points give hints about distillation and crystallization option. Actually, volatilities and solubilities of components in a mixture are needed, but these are more difficult to find. Later, the use of the table will be demonstrated for the PDO case. For now, we will shortly introduce some molecular separation techniques. Water evaporation is a major DSP operation. Also, a major DSP cost source because of the energy required. To minimize energy use, an option is shown in which the feed that needs to be concentrated enters the first of three so-called effects. The contents of the first effect are kept at the boiling temperature by using indirect contact with steam from an external source via a heat exchanger. Water evaporates from the feed and leaves the first effect at the boiling temperature. It is compressed to reach a higher temperature such that it can be used as heating source in the heat exchanger of the second effect. This leads to evaporation in the second effect, and the vapor stream from the second effect is compressed to become heating source in the third effect. To condense the water evaporated in the third effect, external cooling water is needed. So only the first effect needs external steam and only the third effect needs cooling water. Configurations like this one can easily reduce the energy requirement by a factor of 3, but investments in equipment will increase. In distillation, the bottom is heated and the top is cooled, leading to a desired temperature gradient and high energy costs, of course. Liquid flows down and is heating by upflowing vapor, which is cooled in this way. In each stage, liquid components evaporate and vapor components condense, depending on their local volatility, which is hard to predict for many biotech mixtures because of hydrogen bonding. In favorable cases, the local equilibrium of the countercurrent flows leads to very good separations. As mentioned before, extraction should be done using multi-stage countercurrent contact. For liquids, this can be achieved in extraction columns. Raffinate is feed depleted of product. Raffinate has become saturated by the extractant, leading to a new separation challenge. The solvent for an industrial extraction must meet many requirements, sometimes too many. Solvent losses may have to be kept far below 1%. That can lead to distillations of both phases that leave the extraction column, so a lot of extra costs. This picture shows an example. A product or side product in a feed may be removed to a sorbent phase instead of to an extractant phase. Selective sorbents may be found, leading you to a useful separation factor. Sorbent doesn't easily flow and is preferably packed in a column where it is used batch-wise. To approach continuous and even countercurrent behavior, one can use cyclic arrangement of alternating columns. Those are not elaborated here. After adsorption has saturated the column to its end, you also need desorption and the regeneration to bring the sorbent back to its original condition. Sorbent material is too valuable for single use. Desorption and regeneration lead to side streams that are easily forgotten in early design stages. products still must be separated from the desorbent in an additional operation. If we do not adsorb molecules but ions, we use ion exchange sorbents. When the cation is adsorbed, for example, a different type of cation is released in solution. In the example shown, anionic charges are fixed to the adsorbent. Adsorption and desorption can also be seen as reactions, as shown here. Replacement of dissolved cations by H+, and in another column, dissolved anions by OH-, can dissolve the solution because H+ and OH- combine to form water. For adsorption processes, chromatography is an important operation mode to separate complex molecules from each other. For example, proteins. A mixture to be separated is loaded on the first part of the column, relatively much as compared to analytical chromatography. Then, during elution, a solvent is used for some time to flow the mixture through the column, but the mixture components will be retarded by adsorption on the particles that they pass. The components desorb again, but stronger adsorbing components reach the column exit later. In this way, solution at the column exit can be collected per component. In crystallization and precipitation, the solubility of a solute is exceeded, such that this solute tends to form a solid phase that can be recovered. Crystallization is done carefully to give target molecules sufficient time to fit on the crystal surface. Precipitation is much less controlled, causing the target molecules to randomly stick together and leading to inclusion of some solvent with impurities. If the solute to be crystallized or precipitated is an ion, you need to find a counter-ion that has a low solubility product with the target ion to get supersaturation. That counter-ion may be added as salt, acid or base. Any such addition, also addition of an antisolvent, may lead to needs for recycles. In biotechnology, molecular separations often deal with an aqueous solution of product with impurities. To separate these, an auxiliary phase is used that preferably moves countercurrently. To get this second phase, you can use mass input, adding an extracting solvent, a sorbent, precipitating agent, or energy input, like heating to get vapor, cooling to get crystals. Mind that a mass separating agent introduces a new component. We have seen that this leads to an extra separation unit like extractant evaporation or desorption. Energy separating agents are needed to recover mass separating agents. If mass separating agents can be avoided, DSP may be simple. To avoid surprises, I advise to design the structure of the whole downstream process before sizing any of its units operations. Next week, I will show this for the PDO case. See you then!